Today's topic deals with neutralization reactions, which we've already talked about back in the chemical equations and reactions unit. You knew them better as a type of double replacement reaction. So as the name implies, neutralization, it's a reaction between an acid and a base, and the acid neutralizes the base and vice versa. So what happens is the hydrogen ion from the acid combines with the hydroxide ion from the base to produce water, HOH or H2O. And then the second product is a salt. So generically speaking, whenever you add any acid to any base, they neutralize each other at least to some degree, and you get water plus salt. And what the salt is depends on what the acid and base are. So for an example, if I give you any acid or any base, you should know that it will produce water and salt. So we can define salt as the product of an acid-base neutralization reaction. Previously, we defined salts as ionic crystalline solids, both of which are true. So here's a neutralization reaction. Nitric acid in aqueous solution combines with potassium hydroxide. Double replacement, the hydrogen and the potassium trade places or trade partners. Potassium's new partner is nitrate, and hydrogen ion's new partner is hydroxide. So we get potassium nitrate and water, and it balances as written. Okay. Now, here's another acid-base neutralization reaction. This time it's barium hydroxide with hydrochloric acid. And barium's new partner is chloride. There's a 2 here because of the charges. Barium is 2 plus, chloride is 1 minus. And then hydrogen's new partner is OH, so we get water. And there's a 2 there to balance the number of hydrogens. There's 2 there to balance the number of chlorines. Now, another skill you're going to have to be able to have is I could give you a salt like barium chloride, and you should be able to predict what acid and what base produce that salt. So one way to do this would be to just write this reaction in reverse. Barium's new partner, and you'll remember that the water is going to split into hydrogen and hydroxide. So barium's new partner would be hydroxide, and hydrogen's new partner would be chloride. Okay. Or you can merely think of the barium chloride as coming from an acid and a base. The acid comes from the negative part of the salt, and the base comes from the positive part of the salt. Okay. Now, the next lab we're going to do deals with what's called a titration. And we talked about titration way back at the beginning of the year when we learned about burettes. This item down here at the bottom is a burette, and it's used for a titration. And the purpose of a titration is to test the concentration of an unknown solution. So you put the unknown solution in this flask, and you put the known solution in the burette. So the formal definition of a titration is where you take measured amounts of one substance, which is the standard solution, which always goes in the burette, and you add it to measured amounts of another substance that's an unknown solution. So you don't know the concentration of this solution, but you do of this solution. And you see how much of this does it take to neutralize this. Okay, now, in order to be able to see the neutralization, we have to put an indicator. And when the indicator changes color, it's called the endpoint of the titration. Okay, so here we're titrating sodium hydroxide into hydrochloric acid. The salt would be sodium chloride, and then HOH or water is the other. Okay. Now, what does salt water look like? It's clear and colorless, as are these acids and bases. So we need an indicator. Phenolphthalein is the perfect indicator because it's clear in acid and it turns pink in a base. So the goal then is to have the ever so slightest faint pink um, in the end of the neutralization reaction. Now, once again, the standard solution is the solution that we know the concentration for, and then the unknown is the solution that we do not know the concentration for. Now, once you do the titration, then we need an equation to figure out the concentration of the unknown. And that titration is VA-NA equals VB-NB, where VA is the volume of the acid, VB is the volume of the base, N is the solution concentration. It's called normality. And normality is a close cousin of molarity. You remember that molarity is moles per liter. Well, normality is equivalents per liter. So the only difference is to convert the number of moles to equivalents. And an equivalent is the amount of charge in a acid or base. So what you do for an acid, you look to the number of ionizable hydrogens. So however many H's there are in the acid, that's the multiplier. And for bases, you look at the OHs. Okay? And the number of OHs is the multiplier. So for these two, the multiplier would be 1. If we go back to the barium hydroxide, that multiplier would be 2, since there's 2 OHs. For hydrochloric acid, there's only 1 H. You ignore the coefficient, so the multiplier would be 1. Okay, so here's a sample problem. Much like what we're going to do in the lab, you take a very measured amounts of the unknown. So here we have acetic acid, and we use 10 mils of the sample. We titrate it with the base. So we put the acid in here with phenolphthalein. We put the base in here, and we run it until it turns ever so slightly pink. And it takes 15.6 mils of the base, which is 0.5 molar. Okay. So VA-NA, VB-NB is the equation. The volume of the acid is 10. The normality of the acid is what we don't know. The volume of the base is 15.6. And the normality of the base, well, it's 0.5 molar. And since it only has 1 OH, then the multiplier is 1. So its normality is the same, 0.5. So 10, unknown, 15, 0.5. So it'd be 15.6 times 0.5 divided by 10 gives us 0.78 normal. Then to figure out the molarity, we look at the acid. There's 1 ionizable hydrogen. These 3 aren't ionizable. They're part of the polyatomic ion, so they're stuck bonded to the polyatomic ion. So that's the one that gets liberated as an acid. So we just divide by 1 to get the molarity. That's titration. Now, when we're titrating, you can see that the pH doesn't change much. We can add a whole bunch and the pH doesn't change until just before we get the endpoint. Okay, so once it starts to turn to a permanent pink, you have to slow way down, and then you'll see that the endpoint is a faint pink. So you're gonna ask yourself, hey, is that pink or is it clear? And then you'll add one more drop, and just one tiny drop, boom, and it's too far. The nice thing is 1 drop is just a fraction of a milliliter, like a half of a tenth of a milliliter. So the burette is a super precise instrument. All right, so that's it for neutralization reactions. Good luck on the study guide, and have fun with the lab.